we go. So with this problem, we have radioactive decay, and we start with 610 grams of some element, X, and we want to know how long it takes for it to decay to 124 grams. So before I start this, I want to tell you a formula that we're actually going to discuss next week about properties of logarithms. And here's the property. The property is that if you have a log, and let's say it's base b, and it's of anything, say a to the c power, then that equals, that's going to equal c times log base b of a. So it's almost as if the exponent c pops out in front of the logarithm and simplifies it. Now, this works for any log, but this will give us a nice tool to compute this. Anyway, let's go back to this problem. We're given this formula, and notice that h is half-life, and there's 1/2. T is time, and in this problem, we're measuring in minutes. So the half-life itself is 9 minutes. And A is the initial amount, and Y is the amount at time t. So it's all in there, so we just have to fill things in. The amount that we want is 124 grams, and we start with 610 grams. So I've used the 124 and I've used the 610, and that's times 0.5. And t is unknown. We don't know what t is. That's what we have to solve for, and we're dividing by 9. So what I'm going to do with this is, the first thing is, I want to put it into a nicer form. Let's just divide by 610, and when I divide this, the units cancel. We actually have a real, just a number there, and we're left with 0.5 to the t over 9. Now here's where some algebra comes in. You know, the basic trick of algebra is to balance the equation, and if you have two things that are equal and you do the same things to them, then the new quantities will be equal. So what we're going to do is we're going to take the log of both sides. And I'm taking the common log, that's base 10, mainly because that's something that I have on my calculator. And notice that over here, I have an exponent, so I have something of this form, so I can take this exponent and pop it out in front. And I'm left with the simplified equation, log of 124 over 610 equals t over 9 times log of 0.5. And that means that we can use our algebra skills right away to solve for t, because all of those logs are just constants. 9 is a constant, so multiplying things out, we have the common log of 124 over 610 divided by the common log of 1/2, all times 9. And that's something that you can put into your calculator. It's a complicated expression, but you should be able to do it. And we get 20.6862220, at least in my calculator. That's a lot of decimal places, but we really just want it to the nearest tenth. So we want it to the nearest tenth. We have to look one more digit and see 8. 8 is big, so we're going to round up to 20.7, and that is the answer to the nearest tenth. Okay, let's go to the next problem. Over here, we have a similar thing, a very similar equation. We just want to solve for x. So what I'm going to do is I'm going to put it into a simpler form, divide both sides by 1080, and I'll have 0.915 to the x power. And what I can do, same idea, is I can take a logarithm of both sides. We did the common log before, but my calculator also has the natural log. And so we may as well try this out. And let's go back to the purple. So we have 410 over 1080, and we have 0.1915 to the x. And here's where we can pop this out to the front with that law, that very simple rule of bringing things out front. I'll tell you why it's true next week, but we're just going to use it this week. You're allowed to use things that you don't understand, and that makes it all the more interesting to see why it's actually true. But we do have a natural log button on the calculators, and here is 0.915, and so we can solve it, and x is going to be the ratio, this complicated logarithm, divided by 1080 over a simpler logarithm. Okay, and we could put those into the calculator, solve it, and my calculator spits out 10.9033651. A lot of decimal places, but I want this to the nearest tenth, so I'm going to go to the tenth. I have to look at one more digit. 0 is small, so I'm going to round down and find x is 10.9 to the nearest tenth. And on we go. Actually, do you want to see this? Let me show you why that rule is true. And I'm going to do it just with the common log. No, actually any log. B to the B. No, I take it back. I won't show you. I'll show you next week. It'll be more fun next week. So let's try these. We're going to do these without a calculator. There's actually another rule that I want to show you. That if you have a log base b, some base, of b to an exponent, that just simplifies to r. And the reason it's true is the logarithm, it has a bad name. It should be called the exponent function. We want to know what exponent of b is b to the r. It's the rth exponent. But to make this actually clear, let's know that this is exponential form. And we know that every equation in exponential form has a corresponding, sorry, did I say exponential form? I meant logarithmic form. That's logarithmic form. There's a logarithm. But every logarithmic form has an exponential form, and they're equivalent. They say exactly the same thing. Look at what happens when we put this into exponential form. We need to know two things. The base is b, and the exponent is r, and then b to the r, that's the answer. So putting this logarithmic equation into exponential form, we have the base, that's there, to the exponent, that's there, is equal to the answer, and this just says b to the r equals b to the r. That's vacuously true, but that's equivalent to this logarithm identity. So let's work with that. One thing we have to know is, for this first one, is that 625 is a power of 5. It's 5 to the 4th power, 5 times 5 times 5 times 5. So this is the log base 5 of 5 to the 4 minus 3, but that complicated logarithm is just 4 minus 3, and we get 1. Okay. Let's do that with the second one. Log with no base there is the common log. That means really base 10. And 1,000, well, there's 3 zeros, so that's 10 cubed. We want to add 8. And using that identity, that's just 3 plus 8, and we get 11 as the answer. And this next one is going to be the same. ln is really log base e, that's the natural log, and there's e to the 27 divided by 3. Well, log base e just says, what's the exponent of e that makes e to the 27, well, that's just 27. And we'll divide by 3 and get the answer of 9. So there we go. Let's move to this next one, domains and ranges. Here's one that we should know pretty well, that we want a logarithm. And this is one that we should be able to graph pretty well just by hand. Here it is, and there's some important points over here. Here's the x-intercept 1, 0, and you can see that the domain, we're only plugging in x values that are positive, and we could write that in interval notation as 0 to infinity. And the range for this is y can be anything, so any real number, and we write that as a funny R font, or you could write it in interval notation, every number between negative infinity and infinity. So I just want to show one more thing here, that this logarithm function is related to an exponential function. Here's y equals e to the, no, not e, why did I say e? Y equals 3 to the x. And here is the y-intercept, 0, 1, because 3 to the 0 equals 1. And these are really identical. It's exactly the same, it's the same function, just we're reflecting it across this line, the line y equals x. Y equals x. This lets us change to an inverse function. So the log base 3 of x and 3 to the x, one is exponential, one is logarithmic. They're just inverses. And we also see that the domain of the exponential function is all real numbers, and that's the same as the range of the inverse function. And the range, we're only getting positive numbers out of this. Y is bigger than 0, so that's the interval 0 to infinity. And the range is the same as the domain of its inverse function. So that's always the connection between the domain and range of a function and its inverse. Let's go back, go to the next problem. And harder one, we want the domain, range, and asymptote of the function. And for this, you have to recognize that there's a graph transformation going on here. That a simpler function is log of x minus 8, and a simpler function is just log of x, and that's base 10. So let's call these functions g of x and h of x. To go from h to g, this is a graph transformation, shift the graph right by 8 units. And to go to this one, we're going to shift the graph up by 3 units. And that's enough to actually take what we know and turn it into what we're asked. So let me just make a table, domain, range, and asymptote. And we're going to graph the log function. The log function looks just like this. H of x equals the common logarithm of x. And we know that the domain is all real numbers. The range is y is bigger than 0. And the asymptote is a horizontal asymptote, y equals 0. I'll show you where that is. That's right over here. Here's the asymptote, y equals 0. Okay, and so that's let's see. That's part of the table, and we can make grid lines here. So now, moving to G is just the graph of H, but shifted by 8 units to the right. And if you shift the real number line by 8 units, you still have the real number line. You can still put all of those in. But the range, if we shift the range is up or down. Well, we're not going to change that by moving the range up or down. No, actually we will. We're shifting it right, so we're not going to shift it up or down. Up and down is the range, left, right is the domain. And the asymptote, we're just shifting it one way or the other, so the asymptote is still y equals 0. And now for what we're waiting for, the domain, if we shift the graph up, we can still do the same inputs, so the domain will be all real numbers. The range, we're shifting it up by 3 units, so it becomes y is bigger than 3, or the interval 3 to infinity. That's the range. And the asymptote, if we shift y equals 0 up by 3 units, we'll get the horizontal line y equals 3. And so there's the domain, range, and asymptote. There you go. Switch to the next problem. State the end behavior of the function. Yikes. Okay, so we should take a stab at graphing this. And I just want to start with the domain. Remember that there's some things that we have to watch for the domain. And one is we never want to divide by 0. And we never want to take the square root of a negative number. And with logarithms, there's still the same thing. If you have the logarithm of x, natural log or any log, then x must be bigger than 0. So inside there, instead of x, we have 4 minus 2x. So that has to be bigger than 0. So 4 is bigger than 2x. So 2 is greater than x. And so on the number line, we're looking at the number 2. And x can be anything less than 2. So here is the domain. And that means that the end behavior is going to be in this direction, x goes to infinity. And also this behavior, x goes to 2. But we have to approach it from the left, so we'll put a little minus sign in the exponent. And we want to know, how does f of x behave for each of these end behaviors? Well, let's see. As x goes to, that should be a negative infinity. As x goes to negative infinity, negative 2x goes to positive infinity, which means that 4 minus 2x also goes to positive infinity, and the logarithm of 4 minus 2x, we know that end behavior, that's going to go to positive infinity. But the negative natural log of 4 minus 2x will go to negative infinity, and if we just add 7 to that, add 7 to that, that's going to go to negative infinity as well. So we can fill this in with that end behavior. And let's look at the other one. As x goes to 2 from the minus side, negative x goes to negative 2 from the positive side. And negative 2x goes to negative 4 from the positive side. And if you add 4 to this, 4 minus 2x goes to 0 from the positive side. And the natural log of something that's going to 0 from the positive side goes to negative infinity. And so negate that. That is going to go to positive infinity, and just add 7. Add 7 is still going to go to positive infinity. And so here, f of x goes to positive infinity. And that is the end behavior. And that was purely, just purely algebraic. If you don't believe me, then graph it. But you could also see this as a sequence of graph transformations. And each graph transformation is going to change the end behavior in a predictable way. Let's not dwell on that. Let's go to our last problem of the set. We want to find the domain of the function. So the input for the log must be positive, and that means that 4 minus x times x plus 6 has to be positive. So we need to solve that, and this goes back to solving inequalities. Actually, there's a quick way to do this. If you think about 4 minus x times x plus 6, that's a parabola, and it crosses the x-axis at 4, you can see that, and at negative 6. And you can see that if you multiply it out, you're going to get a negative x squared. Where's that from? That's from the negative x times the x. And then there's going to be other stuff. Let's call it stuff. But the negative x squared dominates, so it's going to open downwards. That red, that's nice. So it's going to actually look like this. And you can see that the x values where that's above the axis, where it's positive, is between negative 6 and 4. So the domain will just be the open interval, negative 6 to 4, and there we go. But I want to show you another way to solve this. Another way to solve this is more general. What we're thinking of is the number line, and you can see that we're going to, this function, we want to know where it's positive. It's going to change signs, possibly change signs at negative 6 and at 4. So there's actually 3 intervals that we're interested in. There's negative 6 to 4, that's in between, but there's also beyond 4, 4 to infinity, and negative infinity to negative 6. And each of these intervals, the function is either going to be always positive or always negative. You can see that by the continuity of this parabola, that it never jumps around. If it's positive, it's not going to become negative until it passes through 0, but we know exactly where that happens. So we can test each of these intervals with a test number. For example, the test number 0 works really well in this interval because 0 is right there. And so we want to look at 4 minus 0 times 0 plus 6. And that's 4 times 6, that's 24. Is that bigger than 0? Yes. So this interval is good. By that I mean it's in the domain. X values there will be completely in the domain. What about 4 to infinity? Well, we could pick a number like 5. Keep it simple. I'd never pick something like 5.372, but 5 is simple enough, and there might be a simpler number. That's our test number, and we want to look at test number 5, and so I want to see what happens with 4 minus 5 times 5 plus 6, just setting x equals 5. So I have negative 1 times 11, that's negative 11. And the question is this bigger than 0? No, so this is a bad interval, and this is not in the domain. Last thing, what's a good test number for this first interval, negative infinity to negative 6? Well, something to the left of negative 6. Let's see what happens with negative 10. Negative 7 is also good if you were thinking of that. But we want 4 minus negative 10 times negative 10 plus 6. So we're looking at 14 times negative 4. That's a big number, but I can do it. 5856, this is negative 56. Still the question is this bigger than 0? No, so that's bad. And so this is not in the domain, which leads us just to this one. And so what's in the domain is going to be just negative 6 to 4. We should test the endpoints or consider them. I know that the endpoints will make the function 0. We can't put that into the logarithm. So we want the interval -6 to 4, and we can solve it in several ways. That's it for the rest of this problem set. Thanks so much for watching, and I'll see you next week. Read ahead into properties of logarithms. Figure out what they are, and we'll talk about how to use them and why they're true. Thanks.